The next topic is about unbalanced three-phase systems. So there are two causes of unbalanced systems. So either the voltage sources are not equal in magnitude and or differ in phase by angles that are unequal, or the load impedances are unequal. So usually this is the case. Load impedances are unequal. So if you have for example, a unbalanced Y load with a neutral line, solve for the line currents. You need to apply KVL at these loops, these equations. And now for this case, IN is not equal to 0. So here is a current flowing through the neutral line. For example number 10, determine the complex power delivered to the three-phase load of a 4-wire Y2Y circuit, such as the one shown in this figure. The three-phase voltages of the Y-connected source are VA equivalent to 110 angle 0, VB 110 angle negative 120, and VC is 110 angle 120 PRMS. So the voltage sources are balanced. So the load impedances are ZA 50 plus J80 ohms, GB equals to J50 ohms, and CC is 100 plus J25 ohms. So now the load impedances are not equal. So how do we get the total complex power? So for a 4-wire Y2Y circuit, it's easy for us to determine the total complex power. So why? So if you look at this phase right here, ZA, the voltage across this is just equivalent to this phase voltage VA. And for phase B, phase voltage of this load is equivalent to VB. And lastly, for ZC, the phase voltage across this load is equivalent to VC. So we can use the equation. The complex power for each phase is equivalent to, we have magnitude of the phase voltage squared over Z phase, conjugate of Z phase. We have ZA is equivalent to, SA, so the complex power of A is just equivalent to, we have 110 squared over 50 plus J80 conjugate is equivalent to, we have 7.98 plus G 108.76 VA. So similarly, we can get the complex power at phase B and phase C. So we have J242 VA and 113.88 plus 28.47 VA. So S total just A plus SB plus SC. So how about if the configuration is a 3-wire Y2Y circuit? So this time, since this is a unbalanced system, VNN not equal to 0. So we cannot use the per phase analysis. Now to solve for this circuit, you can use any uh, circuit analysis technique. But for this example, we will use the mesh analysis. There are only two meshes. We have mesh current right here, we have I1, then mesh current right here, I2. So the mesh current I1 is just equivalent to IAA, and mesh current I2 is equivalent to negative ITC, and IBB is equivalent to I2 minus I1. First, let's formulate the equations for I1 and I2. So you have 50 plus J130, then negative J50, then negative J50, 100 plus J75, and this is I1, I2, equivalent to 190.53 or 30 and 190.53 angle negative 90. Now we can solve for I1 and I2. Using the matrix and determinants to solve for the values of I1 and I2, okay, we need to get first determinant of 50 plus J130 J J50 and 100 plus J75. This is equivalent to negative 2250 plus J10750. Next, we need to get the determinant of I1. We have 190.3 angle 30 and negative J50, and second row is 190.53 angle negative 90 plus 100 plus J75. We have 18,882 plus 21,901.79. Okay. And for D sub I2, we have T plus J130 190.53 angle 30. We have negative J50 190.53 angle negative 90. We have 20,005.5 plus J 1276.31. Now solving for the value of I1, we have D sub I1 over D is equivalent to 1.71 angle of negative 48.42. Now for I2, we have D sub I2 over D equivalent to 1.19 angle of negative 101.3. We have the values for I1 and I2, so and also for IAA, IBB, and ICC. So IAA is just equivalent to I1 equivalent to 1.71 angle negative 48.42 years, and ICC is just equivalent to negative I2 1.19 angle of 78.7 years. Then we have IBB equivalent to I2 minus I1, 1.37 angle of 175.31 years. So now the values for line currents. So we can now get our complex power of each phase. Using the values of the line currents, we can now get the total complex power of each phase. We have for phase A equivalent to magnitude of IAA squared times C plus GAT. So this is equivalent to, we have 146.05 plus J2 33.33 VA. And for phase B, we have magnitude of IBB squared times G50. We have 93.85 VA. And max power for phase C is magnitude of ICC squared times 100 plus J25 equivalent to 14131 plus J35.4 VA. For the total complex power of the three-phase unbalanced three-phase loads is equivalent to 287.815 plus J 363.18 VA.